Yeah, if you did it by hand, I'll give you extra credit. I'm kidding, I'm kidding. Yeah, exactly, right? And I'm going to start raising hell in here. Wait a minute. If you would have said that, I would have done it by hand, man.
What if you did it by hand, got the wrong answer, then plugged it into the computer and got the right answer, and then put that underneath?
Then it's all wrong. Then it's all wrong.
Zero.
You get 0 for it. All right, let's get back to what we were doing here. Yeah, that's it. 102, let's get going. Where's everybody? Let's see. Christian or Greg's not here. Amanda or Joe. Okay, yeah, they're not here. All right, so let's get going. We're going to finish up chapter 12 in about 10 minutes, and we're going to start going into chapter 13, which is the last chapter of the book. Yep, that's it. All right, so last class, chapter 12, section 8, what we were doing was we were saying, okay, let's say we have an integral, right, and double integral, or this even extends to triple integrals, and we want to change from one variable, or like from x, y to like two different variables, u, v, that we have to compute the Jacobian and then transform our region into this new variable space. Like instead of xy, we convert it, or xy plane, we convert it into the uv plane. And I did one example. The example that I did, I gave you the transformations, I gave you the change of variables, and then from, oh wait, it wasn't this one, sorry. The one we ended class with was this one right here, where we had this region, and where's my stick? This will work, but where's the stick? Is it in here? Do y'all see it? No? This will work. So I gave us these vertices, and then we transformed it over, and I gave you the actual change of variables, and then we used the fact that the transformations were linear, and then that took lines to lines, and it made life great, right? But the key here is that I gave you the actual change of variables. Like I told you what to do, and then everything worked out nicely. What if you have an integral where you're not given the transformation, you're just given a double integral, and you're asked to find the actual change yourself. So let's just do this. We're doing the double integral over the region D, where D is this trapezoid with these vertices. So I'm going to first sketch the region D for us. The region D is going to be in the XY plane. Lauren, yeah, new ones are here. You picked up your other one from last time? No, is it in here? I don't see it in here.
No, I didn't.
You didn't do it last time, that's right. Okay. Okay, so let me plot these points. 1, 0 here. 1, 0, and then 2, 0 here. And then I have 0, -2, and 0, -1. And so I've got this trapezoidal region here. Do it in different color. All right, so we're trying to do that. Now, that region D is actually not that bad. Like if you look at that region, it's not a type 1, it's not a type 2, but you could break it up into two regions. Like if you split it right here, you could do a type 1 here, type 1 there. Like it's doable, right? Do y'all agree that it's not a terrible region? But what would push us to want to do an actual change of variables here is the fact that the integration itself is kind of a monster. So let me just try and convince you of that. If we had to do this double integral of e to the x plus y over x minus y, we know that if we do type 1 or type 2, depending on how we do it, we're either going to have to go with respect to x first or with respect to y, right? One or the other is going to happen. So let's say we did it with respect to y, then with respect to x. Integrating this with respect to y is not nice, right? I mean, you have y's in both the numerator and the denominator. Do you all see that? That's not going to be an easy thing to find the antiderivative of. Do you all agree or no? Yeah? Does everyone see why that would be tough? Yeah? And then even if I change that to x, it doesn't change because we've got x's both in numerator and denominator. So it's not really something I want to go after, right? So maybe a change of variables would somehow make this a little bit more doable. So now I have to figure out, well, what should I use as a change of variables? And this is where it's up to me. And so I'm just going to try something, and I know it's going to work because I've done this problem before. But I think when I do it, it'll make sense, hopefully, to you. All right? What I'm going to do is I'm going to let u be equal to the numerator of that exponent, x plus y, and I'm going to let v be the denominator. And the whole point of that is if I can get this to the new integral, right? This new integral, I'm going to have u on top and v on the bottom, and then I'm going to have some sort of du dv or dv du, and then the numerator and denominator have the variables are separated from one another, and then the integration should be easier. Follow? As opposed to having the u and v mixed both in the numerator and denominator, it would just be u on top, v on the bottom. So I think that's a natural way to go. And so once I get to this, what I can do right now, I'll let you decide. Would you like me to show the new region in the new space, or do you want me to go solve this for x and y so we can do our Jacobian? Because we have to do both things. So what do y'all want to see first? The region transformed, or these written in solved for x and y? Region first? Okay. So this region is 4 vertices, right? And are my transformations linear? Yes. Okay. They're linear transformations, so it's going to take lines to lines, and actually these 4 vertices are going to become the 4 new vertices in my new space. So I want to take that over here to this new space. This is going to be the UV plane instead of the XY plane. And when we transform the region, I can go back up to my notes here. When we transform the region, our integral goes from being over D. In the new space, it's going to be over S. That's just using the notation we used in class, right? So, yeah, I'm going to move right there. All right, so let's start with points here. Let me take this first point here. That's the point 1, 0. That's my x. That's my y. So converting this over to u and v. Well, to get u, I just add the two coordinates together, right? I just add x and y together, so that just gives me 1. And then to get v, I take the x and subtract the y, which would be what here for us? Take x, subtract y. Just 1 again, right? So in this space, in the xy plane, it's the point 1, 0. In the uv plane, it's the point 1, 1. Let's plot that. And then we have, let's take this next point, 2, 0. When I transform that over to the uv, to get u again, I add the two coordinates together. So 2 plus 0 is 2. And then when I do 2 take away 0, I get 2 again. So 2, 2. Up here. All right. Let me take these 2 points. This one here. The point 0, negative 1, that's the xy. When I convert that over, when I add these two coordinates together, I get negative 1. And then be careful here, because you're going to take, to get the v, you take the x coordinate and subtract the y. So we're subtracting negative 1, which gives us positive 1. So it goes negative 1, 1. And then the last one, 0, negative 2, that gets taken over to negative 2, 2. I'm going to just trust you can do the same thing on that? Yeah. Right? And then let me plot those. So negative 1, 1 is here. And then negative 2, 2 is up here. And I think you could argue, I think you could make a pretty decent argument right now that this region is better but not much better, right? I mean, it is.
So type 2.
It's a type 2, exactly. So this is not a very good type 1 unless you broke it into 3 different pieces, right? It would have to be like that, and then it would have to be between here and here, and then between here and here. That's if you look at it as type 1. But if you turn your head and go type 2, right, our y's are between 2 constants, and our x's are between 2 functions of y. Yes, 2 functions of y. So, yeah.
You just use 1/2 and multiply that end result by 2.
Okay, so the question is, can we just take half of it and then double the answer? That's only okay if we have complete symmetry of what we're integrating, which we can't, with that function, we won't have the symmetry. So, unfortunately, no. All right, good. We got our region. We'll come back to that. What else do we want to do? Let's take those equations. Let's get this somehow, these two, we need to somehow convert where we have x equals some function of u and v, and then the y, we need it to be some function of u and v as well. And the reason we need that is because the Jacobian requires we take partials, right? Partial of x with respect to u, partial of y with respect to u, x with respect to v, y with respect to v. I'll show you the formula again just so you are reminded that right there, right? We need this. So it's partial of x with respect to u, y with respect to v, x with respect to v, y with respect to u. So we need these solved for x and y, and those need to be in terms of u and v. So to do that, I will do exactly what I did last class, and that is, I'm going to work with those over here. What the heck? Okay, I have u equals x plus y, and the other equation is v equals x minus y. And I'm going to kind of move quickly through this. Christian, do you want your old one? Last time? This is the test from last time. Anyone else need theirs from last time? All right, so you have all sorts of choices here. I'm going to take this one, solve it for x, and then I'm going to go plug it in over there, and then whatever I get there, I plug back in here, and I should be able to eventually get to this. So solving this for x, I get x equals u minus y. And then I take this and replace the x with that. So v equals u minus y minus y. So that's just that, becoming that, right? Which is just u minus 2y, like that. And then I'm going to solve that for y. If I solve that for y, I think everybody kind of does this different, you know. I'm going to move the 2y, negative 2y to the left, and move the v over, and then I'm going to divide by 2 on both sides. Or multiply by a half. How about that? I think that's better. Questions? We're good? Good? Come on. We're all right? Okay, so do we have y in terms of u and v? Yes, so we're like halfway there. Now we need x in terms of u and v as well. So I'm going to come back to this, and I'm going to say x equals u, take away y, right? Take away y, but that's y. So take away a half of u minus v, and then distribute that negative half through. So you wind up getting 1/2 u plus 1/2 v. So distribute the negative through, and then collect your like terms together. And then here, I think I'll factor 1/2 out. Like that. X is half of u plus v. Y is half of u minus v. All right, I did all of that so that I could go do the Jacobian, right? So let's do the Jacobian now. Space, space, space. I'm going to get rid of this. We'll keep that there, all right? I'm going to just work the Jacobian right here. So for my Jacobian, I'm going to need the absolute value of, I'll put the formula here, partial of x with respect to u times partial y with respect to v minus partial x with respect to v times partial y with respect to u. I think I changed the order. I think in the formula these are back the other way around, but it's multiplication, so it doesn't matter. So let's take these partials and let's take the absolute value. So partial of x with respect to u. So here's x. Here's y. So the partial of x with respect to u, the derivative of u is 1, derivative of v is 0, so that's just a 1, then half of 1 is a half. So we just get that coefficient 1/2 there. Times, all right, partial of y with respect to v, so here's y. With respect to v, there's a negative in front of the v, so I get negative 1, derivative of that's 0, and then times a half, so I get negative a half. And then the formula, it's a minus. And now partial of x with respect to v, so we come back over here, take derivative of this with respect to v, so we get a 1 there, we get a 0 there, half of 1 is a half. And finally, partial of y with respect to u, which is a half, right? And then we have negative 1/4 minus 1/4, which is negative 2/4. And take the absolute value, you get 1/2. So with this transformation, we have to scale everything by a half to change the variable over, all right? Questions? Yes?
Why did we set u and v equal to the exponent variables?
Why did we? Let me get, when I set up the integral, I'll try and restate why I think, is that the new one? Is that the new one? New one's on the end. These are the old ones to pick up. Yeah, so is that new? Yeah, sorry, let me just get these out of the way. No, you're good. Was that Amanda?
Oh, I think I have.
You got yours? Oh, here, yeah. To pick up, that's this one. Yep. All right. So, do I have everything? I have the Jacobian, right? I know what my new region looks like. You know, we have not explicitly, like, put this into a type 2 format yet, right? So I'm going to do that right now. On this, again, we're going type 2, so we're saying that we have to be careful. And I think I said this wrong earlier. I think I said our type 2, our y's are between something, our x's are between. Actually, we're in the UV plane, aren't we? So our v's are between two constants, right? And our u's are between two functions of v. And it's a little weird, all right? So let's start with our restriction on v. V must be between where and where? 1 and 2, okay? And then our u's, well, to get our u's, we actually have to figure out what the equation of these two curves are. This one right here and this one right here. That normally would be y equals x, wouldn't it? But we're doing things in terms of u and v. So this is actually v equals u, and this one is v equals negative u. So the similarity there is that y equals x and y equals negative x, right? It's just that we're uv instead. But you have to be careful because our u is trapped between two functions of v, so we have to solve each of these for u, not for v. So but this one's easy, right? That one's already solved for u. So this would be our right bound would be the upper limit that we have on u. So what goes here? V. And then on the lower, negative v. There we go. V and negative v. Type 2, right? Type 2. I didn't want to use type 1 because that would require 3 separate sections that I do type 1. So I've got my limits of integration. I've got my Jacobian. I think I'm ready to convert everything, all right? Yes?
With our Jacobian being a constant like this, could we safely just put it out in front of
You could pull it all the way out in front. Yep. So here's my setup. I have the double integral over d, right, of e to the x plus y over x minus y dA. That's the original problem, right? And what I've done is I've changed variables, And now I'm doing the double integral over s of e to the u over v times a half with respect to area. So I've converted that to this new one. That's replaced with u, that's replaced with v, and then we had the Jacobian, and then dA. Now our restrictions for s were over there, so I'm going to set up my double integral. The outer limits of integration on the outer integral will go from 1 to 2. The inner one will be negative v to v, and then it will be e to the u over v times a half, which I'll pull that out on the next one. D what? D what? du dv? Yes. du dv. du dv. You have to go, the outer one here. The constants are on v, so that's the outer integral. Now, back to your question. Why did we do this transformation? Let me do the integration, and I think when I do this integration, you'll see why this is actually a pretty simple integral compared to what we would have had, right? So I think I can get rid of all this now. Yeah, I don't need any of that now. So this equals, all right, we have our outer integral. And now let's bring the 1/2 out now. 1/2, there's the 1/2, bring that out. And now I'm trying to find some scratch work on the side here, trying to find the antiderivative of e to the u over v. Watch the way I write that. du, right? That's what I'm trying to do. So the 1 over v is like a constant, right? 1 over v is like a constant. So this is really like we're integrating like e to, let's say, 4u du, right? Like 4 is a constant sitting in front of the u. Same thing here, the 1 over v is a constant. So what would the antiderivative of this be? 1/4 e to the 4u, right? So you have to go out front and you have to basically divide through by whatever the constant is. So I'm going to divide through by 1 over v, which really means I'm going to multiply by v. So this antiderivative is going to be v e to the u times 1 over v, right? And then plus a constant. Y'all follow that?
Yeah.
You just take the derivative and you can check, right? V is a constant, take derivative, you get back this. Okay, let me get back over here. So I've got v e to the u times 1 over v, my limits of integration. Okay, so I'm on the inner integral. It's with respect to u, so I'm going to be replacing u with these two values. So u is negative v down here, and u equals v up there. And then when I'm done with that, I will integrate with respect to v. And good things happen now, right? Look at how good things become. If you let u be v, may I erase? Yeah, I guess. So that's just me giving myself a chance to actually do fundamental theorem and just plug in. So if u becomes v, that becomes a v, and then v times 1 over v, you reduce that, that's just e to the first power. So you have v in front, e to the first power. I'll put the 1 there. Right, the only thing we're replacing is the u, right? The v's are not being replaced. And then the second one is v e to the negative 1, because when we put negative v right here, we get reduction and we get a negative 1. Any questions there? And there's nothing I can do with that. These are not like terms, because this is e to the 1, this is e to the negative 1. So it really looks like this now. 1/2 integral 1 to 2 of, let me write it. It's ve minus v e to the negative 1 dv. Looks weird, right? It looks weird. That's what it is. And these are just constants, right? E to the negative 1, e to the first power. So I'm just going to take the antiderivative of each of these. I could also factor v out and pull the constant out. There's a lot of different things I can do here. Yeah, let me do that because it'll just be fun. If I take the 1/2, factor a v out of both of these, right? Factor a v, you're left with e minus e to the -1 like that. And then that's a constant, and pull it out of the integral. So I'm going to have e minus e to the -1 outside of the integral, now integral 1 to 2 of just v dv, and that's super straightforward, right? 1/2 v squared. So I have 1/2 v squared, and I need to evaluate that from v equals 1 to 2. And I will be there after this step, I think. Any questions? Okay. Keeping it going. What happens if we plug in 2? We get 4, right? And then half of that, 2. So we get 2 of those, right? And then minus half, right? 2 minus a half. When I plug in 1 here, I just get a half. So we get 2 of those minus half of those, which leaves us with how many of them? 2 minus a half? 1.5 or 3 halves? Yeah. So 3 halves of these e minus e to the -1s is our answer.
Well, we also have to do the fact that we already have a half of the e minus.
I thought I did, oh, that half. Oops, I forgot that half, didn't I? I was talking, yeah, that was my mistake. I put it in here, I got 2, right? Half of that, 1. And then half and half, 3/4, yes. Thank you, Hunter. 3/4. All righty, that's it. Yeah? Now, I don't think I addressed your question yet, because that was a lot of work to take a region that was doable to begin with and turn it into a region that was not much better. But again, it comes to the integration. The original double integral would have been this. And like I said, depending on how we set up the region, this is either going to be a dx or a dy. Which one do you want to go first? Dx? Okay. So just ignore everything and just, like, how would you integrate that? You know what I'm saying? Like, it's not a straightforward integration. Do you all see that? It's not straightforward. You know what we should do? We should go to Wolfram and see what it does. That'll give us an indication of just how hard this integral is. All right? Probably goes to Taylor. Let's see. Integral of e raised to the fraction x plus y over x minus y. And we said with respect to x first? Yeah. So right away you see, yeah, it says here what? What? Right? EI, what's that? It's the exponential integral. What is that? Well, I mean, who knows, right? There's a definition for that, right? And so I think when you see something like that, you say, all right, look, this isn't happening, right? This is not happening by hand. Does that help, like, convince you? Now, I'm willing to bet that if we did a double integral with the limits of integration on it, the computer could get it. It's just it can't give us a general antiderivative, because when you do a general antiderivative with the, like, plus c, right, the indefinite integral, it can't solve it. But as soon as you give it a definite integral, then it can use series. And then once you use series, then it can approximate, and then everything's good. So you could still get an answer, but by hand you couldn't do it. Yeah, so that's the moral of the story there is, you know, you got to try something, right? And so I picked something u and v. right, to separate the variables from one another, and they were linear transformations. Yes?
What is the exponential integral function?
There's a lot of functions like that, and I honestly don't know what that is. I would have to go look it up, and I mean, it's like what we call an error function. It's how you deal with certain scenarios. You turn to this function that helps you get it, right? But even yeah, I mean, we can look it up, and it's not worth our investigation, because that's just one example of something you could get.
Does Wolfram use Taylor series to solve their problem?
For definite integrals, most likely, yeah. Yeah. I mean, almost all computers are going to use Taylor or Maclaurin's, or whatever, some sort of series. Yeah. Now, when they give you like indefinite integrals, like no limits of integration, then they're using something else. That's not necessarily series. That's where the magic happens. All right. That's it. We are done with chapter 12, and we are going to start chapter 13, the last chapter of the book. And we are a little bit ahead of schedule, which is a great thing, because we'll eat up this time for sure.
Are you sure we have to do chapter 13?
100% sure we have to do chapter
This
13.
is what I'm excited for.
Yeah, this is the interesting stuff.
Oh, cool. I'm not excited anymore.
Vector fields. All right, so what we're going to do here is we're just going to establish what a vector field is. All right, that's it. What is a vector field? And then this will just keep popping up through the rest of this chapter. All right. So this is just these are just definitions. So a vector field in R2 in two-dimensional space is defined as follows. First, we have to have D be some set in the plane. So we're in two-dimensional space. We've got some domain or some set D, right? And we will say that we have defined a vector function on this set D, right? We will denote it with a capital F with this arrow on top, that vector notation we used before. Capital F. What this function does is at each point in here, at each point, you give me an x and a y, right? You give me some point in that space. Then what this function does is it assigns a vector to that point. So like there's the point, and now I will assign a vector. So I come in here and I say, okay, that vector. The capital F function is the thing that generates or creates that vector. And then if you move to a different point in the space, go to a different point, there's going to be another vector that corresponds to that point. And your capital F is like the formula that creates the vectors. And so at every single point, there's a vector. At every point in the space, there is a vector. So it's impossible to look at all the vectors, right? Or else it would just flood the entire space. You just arrows pointing everywhere. So we like to look at just some of them. So a good example of a vector field is something like a magnetic field. If you look at this more of like a two-dimensional vector field,